Hello everyone. In the previous video, we had seen an elementary flow called the vortex flow. In this video, we will put a vortex flow and the non-lifting flow over a circular cylinder in order to get a lifting flow. Now let's see how this is done. So first of all, let's look at the equations of a non-lifting flow and then of the vortex flow and then add them up. So we're going to deal with lifting flow over a circular cylinder, for which we say that the flow is the sum of the non-lifting flow and the vortex flow, right? So in a couple of videos before this, I had explained how the non-lifting flow is modeled, and if you recollect or if you refer back, you would know that the stream function associated with the non-lifting flow is given by psi 1, which is v infinity r sine theta into 1 minus capital R squared by small r squared, where the capital R is the radius of the cylinder, which is given by kappa by 2 pi v infinity, kappa being the strength of the doublet. Now this is the stream function of the non-lifting flow. The stream function of the vortex flow, as we have seen in the previous video, would be gamma by 2 pi logarithm of r. Now here we perform a simple manipulation in order to make things consistent. So if you remember, the stream function psi is obtained by performing an integration, and therefore we've actually ignored a constant of integration, which is c. Now for this c, which is an arbitrary constant, I choose a value of c equals minus gamma by 2 pi logarithm of capital R. Now I'll shortly explain why we choose this. So if I substitute this c in this equation, what I get is therefore minus gamma by 2 pi logarithm of capital R. Now this can be simplified because I have a minus sign here and gamma by 2 pi is a common factor, so I can just replace this with logarithm small r by capital R. So these two equations are the equations of stream functions of the non-lifting flow and the vortex flow. Now let's add these two up and see what we get. So I just add these two. What I do is psi equals psi 1 plus psi 2. So what I would get is therefore plus gamma by 2 pi ln of r by r. This is psi. Now from here you can kind of guess why we chose that arbitrary constant in the vortex flow, which is gamma by 2 pi ln capital R. Now if you see in this equation, if you substitute r equals capital R, small r equals capital R, what you would end up is that this term would go to 0 and this logarithm would be logarithm of r by r, which is 1, capital R by capital R, which would be 1, and logarithm of 1 is 0. So we would get psi equals 0 on the surface of the cylinder. So this is performed just in order to make the derivation consistent, and it's a matter of convenience. So now let's proceed. Now given the stream function, we can find the velocity field associated with the stream function. So now as we have the uh, coordinate system here is r and theta, we'll take the approach using the polar coordinate system, for which the components of velocity Vr is given by 1 by r dou psi by dou theta, and V theta is given by minus dou psi by dou r. Now let's perform the differentiation. So let's take Vr first. Vr, if you look at this expression, there's a theta only here, which is sine theta. So everything else remains constant. Therefore, this uh, expression becomes Vr equals 1 by r into dou psi by dou theta, which would be V infinity r cos theta. The derivative of sine theta is cos theta into 1 minus capital R squared by small r squared. Now this r and this r get cancelled. Now that leaves me with V infinity cos theta into 1 minus capital R squared by small r squared. So let me just write this down separately here. So we have Vr is equal to V infinity cos theta into 1 minus capital R squared by small r squared. Right? So for the V theta component, we need to differentiate the expression for stream function with respect to r. So V theta is minus dou psi by dou r. So now let me just take this r inside. So that would give me an r over here and a minus 1 and a 1 by r over here. So I just took the r from outside the braces to inside, and that's what it would give me. Now let me differentiate this expression with respect to small r, and that gives me V theta is equal to minus of, the minus comes from here, V infinity sine theta is a constant because we are differentiating partially with respect to r. Derivative of r is 1, and derivative of 1 by r is minus 1 by r square. So that gives me 1 plus capital R squared by small r squared. Right? Now, if you differentiate this expression, gamma by 2 pi is a constant, and the derivative of r is 1 by ln r is 1 by r. So what we get is therefore V theta is minus of V infinity sine theta into 1 plus capital R squared by small r squared plus gamma by 2 pi r. So this is the flow field associated with the stream function shown in this equation. Right. So now let me erase all of this and just retain the expressions for the velocity vectors Vr and V theta. So now, having found the velocity vectors, the natural course would be to find the stagnation points of the flow, right? So let's set each of these equations to 0, because stagnation points are those points where the velocity components are all 0. Therefore, first let's look at Vr equals 0, which implies V infinity cos theta into 1 minus r squared by r square is 0. Now this would mean either cos theta is 0, which is theta is pi by 2 or 3 pi by 2, because we are looking at values of theta in the range of 0 to 2 pi, and the other possibility for Vr to be 0 is small r equals capital R. So these two conditions would essentially give a Vr equal to 0. Now let's look at under what conditions V theta is equal to 0. So first of all, let's say that we're looking for those points on r equal to r where V theta turns out to be 0. So if I just simplify this explanation, so what I'm trying to do now is that I have this circle where r equals capital R, along which Vr is 0. So on this circle I'm trying to find which are those points where V theta also is 0. So for that I need to substitute r equals capital R in the V theta expression, right? So that gives me V theta is equal to, this becomes 1 plus r squared by r squared being 1. This expression in the braces would be 2. So I would get a minus 2v infinity sine theta plus gamma by 2 pi capital R equals 0. And from here we get sine theta is equal to gamma I missed yeah is equal to minus gamma by 4 pi v infinity R, right? So theta is therefore sine inverse of gamma by 4 pi v infinity into R. So let's look at what this means. So we have a theta which is sine inverse of gamma by 4 pi v infinity R. First of all, this quantity should be less than 1. Gamma by 4 pi v infinity R has to be less than 1, without which a sine inverse operator will make no sense. So first of all, gamma should be less than 4 pi v infinity R for this equation to make sense. Now what does this mean? This means that we are taking the sine inverse of a quantity which gives us a theta, and it's at this theta and r equals capital R that we have stagnation points. Now very simply, in this case, if you substitute gamma as 0, what you would get is theta as sine inverse of 0, which is this point, which corresponds to theta equal to 0, and this point which corresponds to theta equal to pi. So this is the case of the non-lifting flow over a circular cylinder. Now however, theta is not 0 because gamma is not 0. Therefore, what happens is when we take the sine inverse of this quantity, we would end up getting two values which corresponds to I think I've made a mistake here. There's a minus sign. Yes. Now we would end up getting two values corresponding to the values in the quadrant in which sine theta happens to be negative. Now why I say that is I perhaps failed to mention. Now I have taken the sense of gamma, that is gamma being the circulation, to be positive. So that means the vortex flow is happening in the anti-clockwise direction. So if I have to draw it out, so the vortex flow is happening in the anti-clockwise direction, and that is taken as the positive sense for gamma, and in this analysis I'm assuming that gamma is positive. Now, if gamma happens to be positive, with all the other quantities being positive, we would get sine inverse of a negative quantity. Now, sine inverse of a negative quantity can give us two values. One in the third quadrant, which is somewhere here, and the other in the fourth quadrant, which would be somewhere here, right? So, if this angle is theta, right, this angle would also be theta, and this is pi minus theta, right? So yeah, so I hope the what I'm trying to convey is clear. So this, uh, in simple words, what I'm saying is when you have a positive circulation gamma, the stagnation points which are at theta equal to 0 and pi, when gamma is 0, start to move towards each other along the surface of the cylinder. So the this corresponds to gamma of 0, and these two stagnation points start moving downward towards each other. Now, as you can see, when gamma equals 4 pi v infinity r, we get sine inverse of -1, which happens to be this point, which is theta equal to minus pi by 2 or theta equal to 3 pi by 2. So at this point, when gamma equals 4 pi v infinity r, the two stagnation points collapse and become one stagnation point. One stagnation point. Right? So now the natural question is, what happens if this circulation gamma exceeds the value 4 pi v infinity r? In such a case, this analysis will not work, because sine inverse of a quantity which is larger than 1 or -1 is mathematically incorrect. It does not give us any values. Therefore, we have to see what happens specifically when gamma exceeds the value of 4 pi v infinity r. So let me just erase this part. So now we are looking at the case where gamma is greater than 4 pi v infinity r. So for this, what we would do is we will substitute the other solution for Vr to be 0, which is cos theta equals 0. That gave us theta equal to pi by 2 and 3 pi by 2. So these two values we shall substitute into the v theta expression and see along those theta lines of pi by 2 and 3 pi by 2, where is it that v theta goes to 0. So Vr is 0 at theta equals pi by 2 and 3 pi by 2. So now let me substitute theta equals pi by 2 and 3 pi by 2 in the expression for v theta. So if I do that, let me first substitute theta equals pi by 2. So v infinity sine theta happens to be 1, because theta is pi by 2, into 1 plus capital R squared by small r squared plus gamma by 2 pi r. This is 0. Now clearly, this expression on the left hand side can never be 0, because this is a capital R squared by small r squared, which is added to 1. So this is always going to be a positive quantity. V infinity is taken to be positive. Here again, gamma is positive and r is positive. So if you're adding two positive quantities, it can never give you a result which is equal to 0. So we rule out theta equals pi by 2 as being a solution that we are looking for. So we now look at only the case where theta equals 3 pi by 2. So if I substitute theta equals 3 pi by 2 in the v theta expression, what I would get is sine of 3 pi by 2 is minus 1. Therefore, I'll get a v infinity 1 plus capital R squared by small r squared minus gamma by 2 pi r. And now this expression has to be 0. Now, as you can see, this is a quadratic in small r. Now, to solve this quadratic, I first multiply the equation through with with small r square. That leaves me with r squared v infinity, and then I have a minus gamma by 2 pi r and plus r squared v infinity is 0. So this is my quadratic. So let me erase this part. So now if I solve for r from here, what I would get is the solution to a quadratic is minus b plus or minus root of b squared minus 4ac by 2a. So I'm just going to use that straight away, and that would give me gamma by 2 pi minus b plus or minus root of gamma squared by 4 pi squared minus 4ac. So that would give me 4r squared v infinity squared, right, by 2a, which is 2v infinity from here. So let me just get rid of this equation now. By 2v infinity, right? So now if you look at this expression, what you would get is gamma by 4 pi v infinity plus or minus, if I take the 2v infinity into the square root, I would get gamma by 4 pi gamma by 4 pi v infinity the whole square minus r square. So let me just write that down a bit neatly here. So what I would get is gamma by 4 pi v infinity plus or minus root of gamma by 4 pi v infinity whole squared minus r square. So this would be the radial locations at which the stagnation points occur. So if I have to plot this in this figure, what would happen is that I'm looking at theta equal to pi by 2, which is a line like this, and I'm looking at radial locations corresponding to these quantities. So these quantities will essentially yield two radial locations. So one stagnation point will lie outside the cylinder, which corresponds to the positive root, or rather the positive square root, and the other stagnation point corresponds to the negative square root would lie inside the cylinder. So the stagnation points now has shifted out of the surface of the cylinder. So to just summarize, what we have seen is when gamma is 0, which is the case of a non-lifting flow, the stagnation points lie at theta equal to 0 and theta equal to pi. As I increase gamma, which is the circulation, in order to get a lifting flow, the stagnation points start to move along the cylinder towards each other. at a point where gamma is exactly equal to 4 pi v infinity r, the two stagnation points merge and become one stagnation point at the bottom of the cylinder. And if I keep cranking up gamma further, such that gamma exceeds 4 pi v infinity r, these stagnation points now split in this direction. That is, they stay at theta equals 3 pi by 2, but the radial distance change, which correspond to gamma by 4 pi v infinity plus or minus square root of gamma by 4 pi v infinity whole squared minus capital R square. So this is how the stagnation points move around in a lifting flow depending on the value of gamma. So I'll stop the lifting flow for now. In the next video, we will look at what the CP distribution in a lifting flow is, and we will also look at what are the forces associated with the lifting flow, CL and CD associated with the lifting flow. And towards the end of the next video, we will also look at a famous theorem which is called the Kota-Jakowski theorem, which connects lift with the circulation. I hope the contents of this video were clear. If you have any feedback, please let me know, and if you have any questions, please feel free to drop comments below. Thank you.